Hello, everybody. My name is Ali Trollier, and I'm with Eco2. We're going to be starting this broadcast here in just a moment. Please stay tuned. All right, ladies and gentlemen. Hi there. I'm Ali. I really appreciate everyone joining us today on this beautiful Thursday. We're about to have a hurricane down here in Florida, so I'm looking out the window and keeping an eye on things. Things are going so good so far, so let's go ahead and get started. I'm going to take this webcam away because it's distracting me, and I'm afraid it may distract you. So hope you all enjoyed seeing me. And let's get down to business here. Hope everyone can see my screen. If there are any problems, feel free to post them in the chat window. If you've got any questions, please feel free to post them in the question window of your sidebar. Another thing that I'd like to draw your attention to on the sidebar is the handouts tab, where you can find 5 different documents that we're going to describe here today. So, ladies and gentlemen, we're going to talk about some ideas on how to evaluate chemicals versus oxygenation for hydrogen sulfide control in wastewater collection systems. So today I'd like to just kind of briefly give you an overview of what we're going to talk about in this session. And really the objective of this webcast is to provide information to help you understand how to think about oxygenation and how it relates to your system or a system that you may be working on. We're going to talk about the who, the what, the why, where, and how to evaluate oxygenation. So let's get into it. Who are we? Well, I told you my name is, I'm Ali Trollier, and I'm the Eastern Regional Sales Manager for Eco2. I'm pictured there on the left. Eco2 stands for Eco Oxygen Technologies. We're headquartered out of Indianapolis, Indiana, and the boots on the ground are in that photograph there. So from left to right, it's me, and then our engineering director, Kevin Jacobs. Next to him is Ryan Grimes, our Central and Western U.S. Sales Manager. Next to him, we've got David Klidens. He's the president of Eco2 and CEO. And then next to him, we've got Clay Thompson. He's the National Sales Manager. And we're pretty proud that we have been in business for 20 years. I've been with the team going on 4 years, actually. So I'm really happy to show that this company has been here for 20 years. We were established in 2000. And we've got a few different technologies that we focus on at Eco2. But the one that we're going to be talking about today is wastewater, and specifically wastewater for hydrogen sulfide removal or prevention. So let's talk about that just a little bit, kind of a background or the concepts of hydrogen sulfide and wastewater. I'm going to talk about dissolved sulfides, and I'm going to talk about H2S gas or hydrogen sulfide gas. So how does that come about? Well, the problem is that these long force mains and collection systems become septic. The bacteria and the BOD in the water and on the pipe wall consume the oxygen, and after a certain time, the oxygen is gone. And when that happens, you get this insidious process where naturally occurring dissolved sulfates that are fine and don't hurt anybody, they don't smell, they don't do damage, they're naturally occurring, they're dissolved in the water pretty much everywhere you go. But when there's bacteria and there's no oxygen present, those sulfates are reduced to sulfides, dissolved sulfides. I think of these as a ticking time bomb. And then those dissolved sulfides come out of solution as H2S gas, which is the odorous compound, and then to sulfuric acid, which is the corrosive compound. Here on the left, you can see a diagram of that, and you've probably all seen it before. But here on the left is a simplified diagram of a typical lift station and a force main. So when we say force main, we're talking about this full pipe section. A gravity pipe would be where there is a headspace of air. So from the lift station to that headspace, there's no this is where all of the DO is consumed and those dissolved sulfides are formed. And then when it hits this area, that's where the hydrogen sulfide gas and the odors and then the sulfuric acid and corrosion happen. So what do we do to prevent this? Well, we add dissolved oxygen so that this portion does not become septic. And we do not encourage this reaction here. Okay, well, how do we do that? Oops. Okay, well, first let me just talk briefly about why we care so much about hydrogen sulfide. I mentioned earlier the corrosion and everything, but really there's three main components to why we want to control hydrogen sulfide. Number one being safety. We need to keep our workers and our citizens safe. And this table here on the right shows the H2S gas levels in part per million, according to OSHA, the operational safety hazard. And so you can see that a level of 100 parts per million is when you start really coughing, eye irritation. You can't smell it at 150 parts per million. The human nose can detect this down very, very low, like 0.01 parts per million. And so to get up a level of 100, that's very high, and then you stop smelling it over 150, and then the dramatic safety hazards really start as you get higher in these numbers, where you see instant death around a level of 1,000 parts per million of H2S gas. And I want you to remember that 1,000 parts per million of H2S gas is very, very bad. Now, with these levels, corrosion is extremely high. So we've got odor, we've got safety, and then also corrosion is a major factor. Hydrogen sulfide is the leading cause of acid deterioration in municipal water and wastewater systems. Here's a picture of a major failure, a sewer collapse right downtown of a city that we are working with to prevent that from happening again. Look at the cars, the expense, the pump around. These pipes are buried underground and out of sight, out of mind until something fails. Okay, so now let's talk about oxygenation. This is the main thing that we do here at ECO2. And the definition of oxygen is simply dissolving pure oxygen into a raw sewer line or into some other pipe, or even in a tank or receiving water. So oxygen is rather insoluble. It does not want to be dissolved in water just by its natural properties. So historically, it's been a little bit difficult to use, but the historical methods of getting that oxygen into the water include spargers, sprayers, U-tubes, pressure tanks, and none of those really had very high efficiencies or effectiveness. There were things that would get clogged, they would break, they would rag up. Then in 1994, Dr. Speece, who is shown right here on the right, he's one of my heroes, he invented the Speece Cone. That's how we call it in the industry. He humbly named it the downflow bubble contactor, and it can be found described in detail with a lot of different calculations and processes in his book, Anaerobic Biotechnology and Odor and Corrosion Control. Dr. Speece is a professor emeritus at Vanderbilt University and has PhD from MIT, and he really has a lot of insight on this industry, and this was one of the main components of technology that he has invented, and that is how ECO2 was formed. So you can see a couple of photographs here of some different systems that we've done in the past, from large to small, and I'd like to maybe just take a moment to dispel some myths here about oxygenation. And I want to emphasize that it uses pure oxygen gas. It does not use air or ozone. This process using the Speece Cone is called superoxygenation, not to be confused with supersaturation. And the difference there is that with most systems in superoxygenation, we do not want to exceed the saturation point. But there's a lot of oxygen that we can dissolve up to that saturation point, and that's where we operate. So don't be confused with supersaturation. We want to stay under saturation because we want that dissolved oxygen to stay in the water. So we do this we use this technology for raising the dissolved oxygen without bubbles. And that has a few core processes in wastewater for collection systems that we're going to talk about today, for other processes at the plant, and also for effluent oxygenation for meeting DO effluent permits. We've also done several projects in water quality where we're adding dissolved oxygen for wetlands, lakes, and harbors. And that's a whole other discussion, but we've got several systems installed on those type of applications. And but we're going to focus on wastewater today. So when we talk about oxygenation as a technology, you need equipment to get that oxygen gas into the water. And so we call that a dissolution system, and that is required. So when you take a look at the oxygenation process, there's really two main components. You've got the oxygen source, the oxygen gas supply, plus you've got the dissolution system. And pictured here on the right, this is the Speece Cone. This is what's taking the gas and dissolving it in the water. Just a little bit closer look at what that oxygen source may be, the supply of oxygen gas molecules to be dissolved by ECO2. So the supply of the oxygen is oftentimes pictured here on the left. This is a bulk liquid oxygen supply. It's cryogenic, so it's very cold and condensed to a liquid. And then it goes through a vaporizer and becomes a gas so that we can feed it into the water. Now, these kind of systems don't require any capital as far as the oxygen supply tank and vaporizer go, but they're a monthly lease. They have no noise, no maintenance, no capital, and there are multiple different providers in all major cities. On the other hand, you can, if you cannot do this option for a variety of reasons, you may want to consider an on-site oxygen generator. There are a couple of different manufacturers of these systems. ECO2 does not make one. It's a little bit different system here. There's a lot of moving parts and valves and filters. And so there is a capital expense there. They are noisy, so they should be placed in locations where either noise isn't a problem or put into a building. And also maintenance is required with those, changing the filters and doing different things to keep those things running. Whereas with the liquid oxygen, the Praxairs of the world, they do all that maintenance for you, and they fill it and they drive away, and there's no maintenance at all. So into the part that I really enjoy is the dissolution system. So I'm going to show you a little bit about how that works. So we've got a force main, or we'll call it a conveyance pipeline running down underneath the street. So what we would do to add dissolved oxygen to that line is we would tap that line twice. 1, 2. So we would take some of that flow up through the cone, up through the Speece Cone. It would go through a side stream pump just to overcome the losses and get back into the pipe. So this water, this raw, unscreened wastewater, is going up and down into the top of the cone. So this Speece Cone, it may be very large or very small. It all depends on the flow and the oxygen demand and the pressure and several different factors. But just in principle, the flow comes into this cone. And picture this full of water. There's no headspace in here. Now, oxygen gas is being fed into the side. And the water comes down, picks up the oxygen, is completely dissolved, and goes back into the force main. So we've got 3 components for ECO2. We've got a control with the oxygen feed system. We've got a pump, and we've got the cone. The engineering and the setup are specific to each project. Let's take a little bit closer look at what's going on inside the Speece Cone, if you will. Here's a line diagram. So we've got the force main running along the bottom. We tap off of that, maybe take a third or a half of the flow. It depends on the situation. We go through a side stream pump that's maybe adding a very small amount of pressure, maybe 10 psi. Sometimes more, sometimes a little less. But that unscreened wastewater then flows into the top of the cone. Also, the oxygen gas is fed from the tank or the oxygen gas concentrator and is piped over to the top of the cone. And there's no nozzles, there's no baffles. there are no restrictions here. We've just got the conditions of the flow inside the Speece Cone dissolving the oxygen. So theoretically, the flow coming in is at a very high velocity. Now, the buoyancy velocity of these bubbles is not greater than the flow coming in, so they're trapped inside. They can't escape this way because of the water coming down. Likewise, when the bubbles are traveling down and they're getting smaller and smaller and smaller, the velocity, the buoyancy velocity of those small bubbles is greater than the exit velocity of the water. So all of the bubbles are then trapped in this midsection where they're getting mashed up and dissolved. And that is how no bubbles leave the bottom of the cone. Now, this thing is dished. There's no maintenance. There's no fouling inside here. It's hard to believe with raw wastewater, but it is true. So this is coming in the top, going out the bottom, and we have a product of now raw wastewater with high dissolved oxygen and no bubbles. And I emphasize no bubbles because we want to make sure that we don't impact the flow characteristics of a complex piping system. We don't want to be putting undissolved gases into this line, only dissolved gases. So I'm going to show you some typical results. This is a before shot of an H2S logger that was hanging downstream of the discharge point of a long force main in Knoxville, Tennessee. So here are the days. Each mark is a new day on the x-axis. On the y-axis is the parts per million of hydrogen sulfide that was measured by one of these little Odor loggers that was hanging at the discharge or downstream of the discharge of this long force main. Now, I want to call your attention to these levels. I told you that the nose can smell it at 0.01 parts per million, and they're never really getting below 20. They've got, their average is well over 100, and they've got weekly spikes over 1,000. Remember what I told you about over 1,000 before, instant death? So if someone was to hang their head in this manhole, which I never recommend, but if they did, this would be a catastrophic situation. So without treatment, this is what the end of that force main looks like. With treatment, you can see that at startup, this is over the course of maybe 24 hours along the bottom here. So you can see that once that oxygen is fed and the aerobic conditions kick in, by the time it gets down, this is dropping almost all the way to zero on the very first day. So we're not talking about removing biofilm or doing anything magic. We're just establishing aerobic conditions and stopping that sulfide cycle from occurring. As you get further down the line, this becomes non-detectable. This system has been in place for over 12 years, and I know that you could still see results like this today. These are typical, not unusual. All right, now I'm going to transition to where and why one might consider oxygenation as an alternative to chemical treatment for liquid phase sulfide technology. So the number one reason why people want to consider oxygenation is because of the cost to operate this system. Oxygen gas is 10% the cost on average of calcium nitrates, which is often called bioxide. So if you can feed something that's 10% the cost, would it not be worthwhile to consider a capital project and the return on investment to achieve that ongoing cost savings? I think it is. So we want to take a look at how we're going to do that in a minute. But some more reasons on why you would consider oxygenation besides just the O&M cost is the results. Oxygenation can actually eliminate hydrogen sulfide. It doesn't just reduce it or mask it or change it to some other form. You can get zero H2S. Very, very difficult with any other technology or chemical. Also, the oxygenation is a very simple and efficient process. It's very low maintenance. Once you do a capital project and you get the thing installed correctly, designed and set up and dialed in, the controls are automatic and it's very, very hands-off operation. And another one that's one of my personal favorites as a tree hugger is the sustainable technology. It's green. There are no byproducts from oxygen. Very low carbon footprint. Also, by establishing aerobic conditions in all these collection lines, we're stopping a lot of greenhouse gases from being formed. Not just sulfide, but also methane that occurs under anaerobic conditions. So there are a lot of different initiatives that we can check the box here. We're sustainable, we're green, we're better cost, with better results. And so I'd like to just kind of explain how oxygenation can achieve that and where you might find some similar results in your system. So don't get overwhelmed here. This is a table that we've put together based on information gathered through the WEF Odor Gurus. And this document is available as a handout. And you can see that in the handout section of your sidebar on the webcast. We've got this available for you to take a look at and to use it as a reference. And so I'll just kind of describe it real quickly here, but on the left hand of this table, so this left-hand column is the different chemical technologies for liquid phase treatment. Now, I'm not comparing any of these to any vapor phase treatment, biofilters, chemical scrubbers, anything like that. They're different tools in the toolbox, and I think that it's important to distinguish where and when to use each one with the most advantages. And on this table, we're really only talking about those liquid phase technologies, okay? So on the left, we've got oxygen at the top, chlorine, not used very often, but I had the info, so we put it in here. Hydrogen peroxide is another chemical, and we've got some information there on that. Calcium nitrate is probably the biggest use. Then iron salt. And then at the bottom is mag hydroxide, or ThioGuard, as you may know it. Okay, so for each one of these chemicals or technologies, we've categorized and we've summarized some information for their application, the storage and handling. The next column is neat because it says, what is the best this chemical can do? The lowest H2S achievable if you use that technology. Also, we've got information here on dosages and some key factors on what that dosage is dependent on. Some are dependent on flow. Some are dependent on dissolved sulfides. Oxygen is dependent on a combination of those. Also, we've got a product cost here, so you can figure out your dose, multiply it by your flow or whatever else it's dependent on, and then multiply it by your cost and get some sort of idea of what this is going to cost you to operate each different technology. And then we've got a column here for pros and cons of each chemical. So you can see that there are several for each. I'd like to just ensure that each of you have the opportunity to download that handout. And if you don't get it here, please feel free to email us and let me know if you see any errors or need corrections. But we did collect a lot of this information from the recent webinar or webcast by the WEF Air and Odors Committee, featuring Dick Pope and Bruce Cutter. I'd like to give a little shout out to those brilliant gentlemen for helping with the information on dosages, costing, costs, and experience. So all that table, all that stuff, it's like really neat to have, but what if you were to apply those numbers to certain scenarios? So that's what we did here, is we said, let's take a look at what that annual cost would be for all those chemicals on 3 different scenarios. So we made up scenario A, it's a force main of 1.2 mgd and yada yada. Scenario B and scenario C. So we used these numbers that really we just kind of picked out of the air just to say, well, what if it was this and that and that? And then we plotted these on this graph here. And so you can see the different bars represent the different chemicals that were listed in that table. Let's take a look at this one here on the right. So this is a force main 10 mgd that we just really made up. The green bar represents oxygen. The yellow is chlorine. The blue is hydrogen peroxide. And the purple is bioxide. So that's what we are usually being compared to. Bioxide versus oxygen. These bars tell a story here. This is a dramatic difference in annual operating costs. Now, I would like to point out the fact that with this green bar does come capital expense. I have not incorporated that or amortized that cost into these annual operating expenses. Please just note that this is purely operating, and if you are doing a return on investment calculation, you would need to include capital expenses. We'll talk about that a little bit more, but I just wanted to show this one. This graph is also available in the handout. So I talked about setting up 3 specific scenarios. And when I talk about oxygenation, people may say, well, I've got H2S problems all over my flat plate of spaghetti looking collection system. Can I use it everywhere? Where should I start? Well, the answer there is it may work really great in a lot of different applications, and it may not be a technical fit for other applications. So I'd like to focus in on where oxygen has the best fit, and that is a handful of locations in a collection system. So we might consider first, where are the hot spots or the high hydrogen sulfide gas locations? Like you may say, okay, out at lift station 25, we've got a major odor problem. We've seen corrosion. Let's look upstream of that point. Or say you've got a location that has a very high chemical requirement. Maybe you've got one lift station that you're using $200,000 a year in chemicals. Let's think about maybe what we could do better, save money, better results, better for the environment. That is probably the best spot to start. Also, a lot of our applications are done in force mains because long force mains create high dissolved sulfides, which then create high hydrogen sulfide. Also, isolated lines are key for oxygenation because when we're treating at an upstream location, we want limited downstream added inputs because those inputs would then not be treated. Also, higher flows have a higher potential for chemical savings. So it's just a factor of increasing returns as flows and municipalities and chemical usages increase. Also, we're looking at large diameter gravity mains because you can dissolve up to 4 hours worth of dissolved oxygen into a gravity main. I'm going to tell you how I came up with that number in a little bit, but I just want you to keep that in mind. Up to 4 hours with no pressure is still a technical fit for oxygenation. We don't need to be an enclosed pipe, and it doesn't need to be at pressure because you can consider that saturation value under a variety of conditions, not just under pressure. Also, I'd like to just highlight where corrosion is a concern. Odors are very easy to identify and can be expensive to treat, but corrosion is very, very difficult to identify and to justify the expenses. However, the cost to repair those corrosion damage is often much greater than the cost to treat odors. So it may be advantageous financially to look at treating for corrosion and enjoy the benefits of the odor prevention, because treating for corrosion means you have to get to a much lower level of sulfides to affect that rate of corrosion. Say less than 10 parts per million to dramatically affect the rate of corrosion. You may also have take a look at this hydraulic profile. So you may have something that looks like this. It's a very long force main. Yeah, it's isolated. Yeah, it's got good flow. Yeah, it's a hot spot. Yeah, they've got corrosion, but it's so long that the pressure in that line did not allow that much oxygen to be put in there. So what did we do? We split it into 2 sections. So you may want to look at multiple injection points for long retention time systems. Or if you've got a long retention time, you may want to consider treating just upstream of a problem area. For example, maybe you've got a 10-mile-long force main that's made out of a non-corrosive material like PVC. And you don't really need to prevent corrosion all the way, but you need to prevent the headworks at the end. So if you back up a certain amount of time or length, and in oxygen's case, it takes up to 30 minutes to oxidize those nasty little sulfides before they hit the problem area. So we would say, back up a certain distance and just treat the discharge. So there's a lot of different ideas here. Now, what do we do with all those ideas? Well, we got to set them up and knock them down. And we have a design data checklist that is really our key to collecting the information for a specific location and then determining if that location is a good technical fit for oxygenation or is it not. So this is one of the other handouts in the handout section on your right-hand side panel. And I'm not expecting you to really see this, but this is what it looks like. And it's just going to say, what is the pump station? What's the diameter of this force main, the length, the head pressure, the flows. We need to determine those values so that we can calculate a retention time and a dissolved oxygen demand, determine if this is a fit. What does that look like? Let's dig into how we evaluate a specific location to determine if it is a good technical fit for oxygen and examples on how to do that. So when we talk about, is it a technical fit? This is something that we must determine before we get into all the cost analysis. We say, can we do this here? And if it's a yes, then we say, all right, let's evaluate those costs. And so this is how we do that. To determine the technical fit, you've got to determine the oxygen demand of that section. How much oxygen do we need to keep that section aerobic? And then the saturation of that water. How much oxygen can be dissolved in that water based on the pressure and the temperature and the different characteristics. So these 3 pages are part of a handout. The last one I think I'm going to mention here, but this 3-page handout goes into detail for those oxygen demand calculations and the solubility saturation calculations, and then also some references at the end. So I'd like to draw your attention to that. If you want to get into the nitty-gritty, that's where you can find it. But I'm going to show you the keys to the bank anyway. I'm going to summarize it here, and then I'm going to follow up with some simplified rules of thumb on the next page and do some example numbers. Okay, so bear with me here. This is going to sound a little complicated, but it's actually very simple. To determine the oxygen demand of a specific section of pipe or a tank or whatever it is, you have to add these 3 things. You add the existing dissolved sulfides that you have to get rid of, the aerobic conditions for the retention time there. So we take the oxygen uptake rate times the hydraulic retention time. So we say, all right, this is how much time we've got, and this is the rate at which the bugs are going to consume the dissolved oxygen. That's the dissolved oxygen demand to maintain those aerobic conditions. Then you want to add to that any desired residual dissolved oxygen that you may want at the end of this section of pipe. So you add those 3 things, and you get the sum of that is the total oxygen demand. And then you take that number and you say, well, can I fit that into the saturation or not? Can we dissolve the necessary volume of oxygen into this water at its current conditions? And then can we maintain that saturation through the pipe as it goes over the hills and down through the valleys? So what we want to do is we want to look at the hydraulic profile, and we plot the DO content and the DO saturation at all points along that hydraulic profile. So that's where we live, and that's what we do. We are always determining DO demand and then evaluating against DO saturation. This is what that may look like with some simplified rules of thumb. These are not the end-all, be-all numbers, but I'd like to just kind of give you an idea of how to think about this. So the two green lines here, DO demand, DO saturation. How much do we need versus how much can we do? And that's just based on science. That's not saying efficiencies of this or that. That's just Henry's law, solubility, and the amount of dissolved gases that a water will hold in solution. Okay, so first off, DO demand. We're going to add up these two things. What do we need to remove the dissolved sulfides, and how much do we need to prevent the formation of more sulfides? Okay, so to remove the existing dissolved sulfides, it's a 2-to-1 ratio, 2 oxygen to 1 dissolved sulfides. So let's say we've got 1.5 milligrams of dissolved sulfides in a wet well right before we add oxygen. So we say, all right, we need 2 mils times 1.5 mils. We need 3 milligrams per liter of DO to remove the existing dissolved sulfide. We're going to add that to the DO we need to prevent sulfide formation, to maintain those aerobic conditions. So you take the HRT times the OUR, the oxygen uptake rate, is on average 10 milligrams per liter per hour. And that's an industry standard for most wastewaters in a pipe. So that oxygen uptake rate is saying for each hour we spend in the pipe, we're going to need 10 milligrams per liter of dissolved oxygen. Otherwise, we're going to go septic. Okay? So let's just say we had an HRT on this pipe of 8 hours. So 8 times 10 is 80. So we need 80 milligrams per liter to keep aerobic conditions. 80 plus 3, that whole deal. So we need a total DO demand of 83 milligrams per liter. Now let's see how much we can get in. Let's say we've got 65 feet of head pressure. Well, my rule of thumb is you add the feet of head to 40, because at atmospheric conditions, you can dissolve 40 milligrams per liter of dissolved oxygen with 0 pressure. So add 40 to however many feet of head you have in the pipe, and that's roughly what the DO saturation level is. So just going with these simplified rules of thumb, we've got a saturation point of 105 milligrams per liter that we could dissolve if we wanted to, but we only need 83, so we are good to go. That is a technical fit. Okay, now let's get into another example. So here I've got a map of a very large collection system that I worked on recently here in Florida. And just to kind of show you what's happening, this line, this light gray line diagonal through the map, is called the turnpike or the freeway. Now on the left side of the freeway has been built out, and it's an established community. They've got pretty good control on their sulfides in this area up to this point where this first green arrow is. Now on the other side, this is all new construction. It's a very high growth area. Affluent area, and so the consultants have been requested to ensure that all the points along this line that run right next to the freeway are kept free from corrosion and odors. And so what we're going to do is we're going to take a look at this line that I just pointed out, and I want to show you why, because we talked about isolated lines. Well, look at this line. This yellow line goes from here all the way over to here with no additional inputs. But then here, we're getting a whole system full of inputs at this point. So we're going to look at adding more oxygen by another system right here. We might call it the midpoint. Down here, we've got additional inputs with additional downstream force mains. We're going to talk about this being a third location of investigation. So I've got 3 fairly isolated force mains. And we're going to take a look at what that what those numbers look like. So remember the design data checklist that I talked about? It's like 20 questions for each location. It seems arduous, but when you get into it, it's actually quite simple. So here on the left are all of those different parameters that I mentioned earlier: the diameter, the length, the pressure. And so we want to determine those values for each location. So I'm going to focus you here on this first, or the second column rather, called the yellow line at SSU number 11. And I appreciate the folks for letting me use this information. This is real life data. I didn't just make it up. So here you can see this is a 20-inch force main that goes about a mile. Got about 100 feet of head when it's pumping, and about 84 feet of static head. You can see I've got the flow rates for this one. I've got all the information for each different line. Now, down here in the second part of this table are the calculations that we've started to use for the design of this initial proposed system. So here we've calculated the retention time from the flows provided to assume an average HRT, hydraulic retention time. Then we try and forecast what the maximum HRT is during low flow conditions. So the more retention time you've got, the more oxygen demand you've got. It makes more sense because the longer that flow spends in the pipe, the more sulfides it would generate, or the more oxygen it would require. So if we can design for the maximum or the worst case HRT, then that means that we're going to be a technical fit for anything less than that. Sidebar, sorry about that. So with this yellow line, we said, okay, we figured out an HRT, and I did this. I said, what's the DO demand? Okay, 39 milligrams per liter. What's the DO saturation at that spot? 120 milligrams per liter. Well, I could put in a lot more dissolved oxygen than I really need. So this is definitely a technical fit. And you can see each of these other three lines were also a technical fit. And so I'm going to go to the next page, and I'm going to show you what some of the costs are and the comparison costs. So remember these. This one has just significantly more flow and significantly more time. It requires 49 milligrams per liter of dissolved oxygen. We could get in 86 if we needed it. So this is what the Speece Cone system would look like for each one of those. So for the yellow line location, it would require a 4-foot in diameter Eco2 Speece Cone. The side stream flow would be this. You'd have an 11 horsepower pump, all that. Put that into cost. So what is it going to cost to pump that pump, maintain it, buy the oxygen, pay for the tank? It's only going to cost $22,000 to operate this yellow line system, not including capital. The capital expense for this one was between $300,000 and $400,000. And so if we take these operating costs with the capital expense, we can determine a return on investment. So I calculated the return on investment over chemical savings, because that's something that is tangible and we can define it. So at this yellow line, we use the potential dissolved sulfide generation and the calculations used for predicting sulfide generation, and we use the dosages from the table we provided earlier and the cost for estimating an annual bioxide cost for each one of these locations. So here we've got a cost savings of $68,000 a year. So to use bioxide on the yellow line, it'd be $91,000. To use oxygen, it was going to be $22,000. So just on this one line, it would be a significant savings every year. Factor in the capital expense. This one has a payback of 5.5 years. This is one of the slower paybacks that I've seen. For example, this next one, the gold line at this next location, that has dramatic savings because it was a lot longer distance, a lot higher flow. It makes sense. and a lot faster payback, because the Eco2 system didn't need to be that much bigger, but you could save a lot more, so the payback is faster. Now, the reason I wanted to show these to you is to kind of give you an example of how to think about comparing oxygenation to the other technologies. Factor in the capital cost, because it's not just so simple as putting out a tank and a pump. You've got to have this Speece Cone system or other dissolution mechanism. So when you talk about evaluating the technologies, it's important to consider these factors. The goals for treatment. Are you trying to just prevent odors? Are you trying to affect the corrosion rates? Also, the O&M cost savings. That's a big one. That's where I live, is trying to save people their O&M budget. If you do a one-time capital project and you can see repeated annual operating budget savings, that can be a significant advantage for a lot of municipalities and utilities. Another thing I want to just focus on ever so briefly is the growing initiatives of our clients and municipalities. They're being held to a much higher standard with safety and odors, but also there's an increased focus on infrastructure. And we've got an opportunity in our industry right now where there are new financing options that are becoming available that are focused on infrastructure repair and protection. And that would include wastewater collection systems. And so I want to encourage you all to think about odor and corrosion as infrastructure protection. Also, very important to a lot of our clients is the environmental sustainability and financial sustainability. It's a lot of big words there, but I think that they can really have meaning in a world where you're constantly trying to find the best solution, the greenest solution, the best results, and normally those don't come at the lowest cost. But with oxygen, there may be an opportunity to do that, because we have seen several applications where we are providing the best solution for the environment. We're achieving optimal results, all while saving the clients money year after year. So with that, I'd really like to just kind of close this out and draw your attention to some of the references and the resources that are provided here. Again, some of the information that's provided in the table was digested by me through the Air and Odors Committee, which I am a member of. The West Air and Odors Committee had a webcast in April of 2020, hosted by Mark Perkins and presented by Dick Pope and Bruce Cutter, and that's where I got some of that dosage and cost information. Also, I'd like to give a shout out to all of my friends and colleagues that were involved with their blood, sweat, and tears in the new update of the Engineering Design Manual, MOP 25. Kudos to the team that put in all the hours to getting that done. It's now available, I believe, and you can find superoxygenation in that manual. Also, we've got a variety of handouts here that I've mentioned. And if you don't get anything there, please feel free to reach out to us on a one-on-one basis, or maybe you'd like to listen to this again because you just can't get enough. Please reach out at any time. Also through our website, case studies, of course, the Dr. Speece book, and our references. And here are the contacts for the team: Clay Thompson, Ryan Grimes, and myself. Now, I would like to just take this time to invite anyone who would like to step off and break away here to go ahead and do so. We're going to close the official part of the webcast. And I really like to say thank you to everyone for your attendance and your engagement and your interest in doing things better and trying to find new ways to do those activities in the best way that we can for the environment and for our constituents. I'm going to open up now to any questions. I don't think that we've actually had any questions appear, but if anyone does have any questions, please post them in the question windows now, and we will go through them one by one. If there are no questions, I invite you to sign off with all of the gratitude in the world for joining us today. Well, it looks like we have no questions. Hopefully that doesn't mean that no one heard any of this. But again, I appreciate everyone for coming, and we will close the session now. Please feel free to reach out directly with any questions or engagement you'd like going forward.